Hi everyone. So what we're going to do now is complete the building of a phylogeny in R. So we're going to do a parsimony phylogeny. That means it's based on shared derived traits, and actually it's going to build a neighbor joining tree as well. I'm going to start from scratch just so you and I are in the same place so you know what things look like. So the thing that you have to have set up ahead of time for R is that you need a folder where you're going to put everything. So on my desktop, I made a data files folder. You'll notice that data files doesn't have any spaces in it. Your folders can't have spaces in them. This is an old feature about coding that just hasn't died. Okay, so that is what I'm going to use. I am going to actually use this file here, which if I open it, let's look at it. So I opened it in Notepad. Notepad's going to be super easy to use for you, or super useful. If you have a Mac, you can use Text Strangler or whatever the newest version of Text Strangler is called. This is my alignment I made for muscle, for the muscle assignment. So this is 5 human and or mammal example or organisms, 5 mammals that all, and this is Hox gene 4. So the Hox gene unfortunately is so similar, well, which is fortunate because it's one of the ones that builds your spinal column, and it sets the fact that you have 4 limbs and those kind of things, so they're very conserved. But this also means that these there's very little variation, but that's okay. So this is my FASTA file, hox4 fasta.fa. FA is FASTA, or it could be .fasta. It doesn't matter. Okay, so that is what I already had. If you did not download this during your muscle assignment, open your alignment back up and then hit download. It might make you a file. If it doesn't, it'll open a screen and it'll look almost exactly like this. You'll just select it all, copy it, and paste it into a notepad and save it. Okay, so I have that. And then I'm going to open RStudio. Also, you have the R version and the text version of this How to Build a Phylogeny. If I open the R version by double clicking, it's going to open this directly up in RStudio. So here it is. Now, one thing I will say is that because my computer has already done this, it's stored in the memory, like how to do this activity. But this pane up here is your log. Your log will already have this information in it. Now, if you double click on that thing, if not, you can just type directly into your log, or you can type directly into your coding space down here. It's completely up to you how you want to do this. Okay, this is your log panel. So this is like where you would want to kind of edit things. I have notes. That's what all the green is. There's some other activities that I've been working on in there. This is where everything's actually working. Down here are where you can see what your files are. And then if you made plots, if you need to install packages, which we do, if you need help or whatever, is here. And this one kind of shows you what's happening as you go. Like if it calculated something, this stuff should change a little bit. This is all stuff from a different day, but I don't know how to clear it, and so we're just going to leave it. Okay, so we've opened RStudio. You either have this file here open, or you have the text here that you can copy and paste out of, really. It's the same. It's kind of the directions, okay? You have your file ready, and so you're going to press Session, Set Working Directory, and then choose Directory. Mine is this data files file, so I did that. You'll see here it did that in blue down here. Doot, doot, doot. And actually, if then I pick files, here are my files, so I can find them. The one specifically that we're going to work with here is this hawk4 fasta.txt file. Okay, pay attention to the ending of your files, because if you wrote it in Notepad, unfortunately, it adds a .text to the end. That's fine. You just have to know that ahead of time. Okay, so I've set my working directory. The next thing I need to do is make sure all of the packages that need to be installed are installed. So that's just calling up what kind of analysis you're going to do. R can do so many things that it's really important to make sure you have the right package open. Okay, so then you're going to, you can, if you're working in this window, select these and press here. I'm going to save one out so I can show you what to do if you're not working that window. Press run. See how it sent those down there? Uh-oh, and it's kicking me back some errors. It did some of them. It didn't like all of them. Okay, but that's okay because there's another way to do this. So you go over here, packages, and then I really need this bio installer to install. So I can just click on it there. There we go. So it installed. It says there's a newer version, but this version works, so I'm just going to leave it. It's completely up to you. So we'll all kind of have to play this game a little bit to see if we got everything installed. So you can also click, we're going to use bio installer, which is just C++, in case you know what that is. We're going to use ape. We're going to use sequin. Here. Boop. And we're going to use Fangorn. I don't know how to pronounce that, but that's what we're going to use, Fangorn. Okay, so I have those all installed. If they're not options here in this package window, you would go up here and you would type it in, 8. Oops. And there it is. And then you would hit install. And it says it's already running. And so then I just hit cancel. But so that's another way you could do that. Okay, so also the libraries are loaded. Oh, what I didn't tell you is BioInstaller C, BioC installer is the first one you need to install. Okay, because it's going to read C++, which is the language that some of the other ones are written in. I don't know why it does it that way, but it does. Okay, so now we should have everything turned on. You'll know later in the game if you get an error if you failed to turn something on, and then you just have to turn it on. So that's not that big of a deal. All right, next we're going to call up our file. This, honestly, is one of the hardest parts of R. It's just getting your file into the R and making it an item that R is using. Once it's in there, it's no big deal, but getting it in there is kind of a pain. So we're going to do it like this. You can, again, either select this and hit run, beep, but I don't want to do that because I want to show you how to do it. So we're going to type down here in this window. Maybe I can make this window bigger. I don't know if that actually works in this. Tools. View. Zoom in. Oh, I have to hit double plus. Okay. Control plus plus. Nothing happens when you do that. Okay. So, here we go. So, I'm going to name my item hawks_4. Alright. And so, I'm making an item. That's what that first thing is. And then, to put in this item, that's this arrow button. So, it's the greater than, and then the minus, which ends up making an arrow. Put in this item, read dot D, and what I really like to do, just to know that I'm not screwing things up, is let it autocorrect. So read.dna. Now read.dna, if you let it autocorrect, it's going to tell you exactly what kinds of things it needs to know. So that's great. So then we hit enter, read.dna, it built its parentheses for me. It wants the file name in quotation marks. So that's Hawks for FASTA.fa.text. And I can see exactly what the file name is over here, Hawks for FASTA.fa.text. In some universes, you could just click on this and it would pop into there, but that's not the universe we live in. So, and then comma, and we need to tell it the format. Okay, and then we want it to do this, and it did it. And see, something over here changed. I didn't see what it was, but something moved over here, and oh, here it is. Hawks for DNA, raw, blah, 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 blah. Okay, so it's seeing something. And just so you know that it actually loaded it, you can tell it to print Hawks_4. And here it is. It has those, each alignment sequence or DNA sequence is about 2,381 characters. There's 1, 2, 3, 4, 5 taxa, and there's a composition of approximately equal. There's a few more C's than I would like, but that's okay. Great. So we did that. Okay. Now, the next hardest step is turning that into phylogenetic information. So what you're doing here is making that character matrix. Putting the traits, you're telling it what the traits are that you're going to build your tree with. So we're going to call that Hawks for phydat. Just so we know exactly what it is. Hawks for phydat. Okay, I'm not going to capitalize those. Okay, so to put in that item, we're going to run phydat. Oh, there we go. And then we're going to tell it what file or what item. So Hawks, yep, see, Hawks_4. And the type of information is DNA, and the levels equal null. I can tell you right now I don't know what that means, but it's a very important statement. Basically, it means we don't throw anything out. Sometimes you throw things out. We're not going to do that. So then you hit enter. If you get an error at this stage, like for instance, I got an error many times saying that there was not the right number of characters in the tree, in the matrix, then you need to go back to your muscle alignment and copy and paste that again, because maybe you skipped like either the first character or the last character. That's what my problem was for a long time. Once you got this in, now you're ready to roll. We can do any type of data analysis now, okay, with phylogenetics. So I have that. Now, if we were going to build a big phylogeny, so I'm right here. We just did this. We put our data in. If we were going to build a phylogeny for publication, you would need to do a model test. So I'm just going to show you how to do that really fast. So model test, oops. So what this is doing is looking at how the DNA varies between your taxa. So like the sequences, model, capital test, yep. And then, oops, I did too many parentheses somehow. Hawks, yep, Hawks_4, phydat. Okay, so I'll show you. So it's just going to show you how those traits vary. We already know that there's not equal base pairs. So the simplest model is that there are the same number of A's as there are C's, as there are T's, as there are G's. Now, we already know that A's and T's should pair up and C's and G's should pair up. So you should have, this should be complementary in some way, but there's not equal ratios because then it would be 0.25, 0.25, 0.25, 0.25. So we know it varies a little bit. That simple model that is called Jukes-Cantor or JC, which you'll see here in a second. I'll show you. Okay, so it's running this. See, here's JC, which is Jukes-Cantor, and then F81, and then K80, and then HKY. All of those are letting something vary. So saying that there's a different number of transitions and there is transversions and all of these different things. The most complicated model is GTR plus G plus I. That I doesn't make a difference, so really it's GTR plus G. Which if you were running a Bayes tree, typically that's the model you're using. Now, so it ran this, okay, and we want to look at it. So we're going to do, I believe this tree, this, we're going to say print. Oops, I'm not typing. Okay, and see, so here's all the different models. There is a diagram on Blackboard that shows you what these models mean. If you ever want to talk about that, I'm happy to, but it's literally not something you need to know. These are different statistical testing to show how well the data fits that thing, and what you're looking for is the drop. So I like to use AIC, and so I look at these numbers. They are going down, 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 down. So the lowest one is this one, which would be model HKY plus I. And then they go back up. Okay, and so that's actually true, yeah, for this. Oh, these are lower over here for log likelihood. This one, HKY, is the lowest for that parameter. That matches up with that one fine. Yeah, so these jump around a little bit. Everybody kind of has differing opinions. There's other ways of looking at how well the model fits later once you've run it. But in this case, it doesn't matter at all because you'll see we're just going to use F81 as our model. Okay. Basically because for the tree we're going to build, it actually gives you 3 different choices. Even though it looks like you have a lot of choices here, you don't. So we need to build a distance matrix. This distance matrix will compare those base pairs and say where the changes are, and then who has shared changes. So that's the difference between the neighbor joining tree and this tree that you're going to build, is that the neighbor joining tree is not based on shared derived traits. It's just based on overall number of changes. So that's the really important step for evolutionary history, shared derived traits. So we're going to build this tree, or this distance matrix. And I'm just going to tell it to run. Boop. And it did that. So DNA underscore distance, that's our, it's doing like a kind of a really short matrix math there. It's using the phylogenetic data, and it's doing model F81. F81 is like, allows the number of transitions and transversions to vary. It's up here, so it's fairly simple. They get more and more complicated, and that's because the math associated with building like a Bayesian phylogeny is much more complicated. Not important at this moment. Okay, this is our distance matrix. Now we use our distance matrix to build our actual trees. So now it's taken that matrix that we saw before. Let's go back up. Oh. We didn't see it before. Print. Oops. Okay, so it's comparing how many shared changes does it have to this one, or how similar is it to this one, to this one, to this one, to this one, right? And then so to itself it would be 0. That's why there's nothing up here, so it's kind of a one-way table. Okay. Now we're going to build an UPGMA, which is a parsimony tree. Okay, so it's saying like the simplest answer is most likely the correct answer. That is what parsimony is based on. It gets more complicated. That's why we have maximum likelihood and we have Bayesian. But parsimony just says the simplest answer is most likely the right answer. So we're going to build a Hawks for parsimony tree based on our distance matrix. Oh, I typed some weird stuff in there. And the parsimony math. We're going to run that. Okay, let's see if it made it. I don't think I printed anything yet, no. And then we're going to also do a neighbor joining tree. This should look exactly like the neighbor joining tree you made in Muscle, because it is the exact same math. In fact, apparently you can run Muscle in R, but when I say you, I really mean the people who design Muscle, because nobody else seems to be able to get it to work. Okay, and then we're going to plot those. So plot is a general command. It works for almost any program. And when I type plot, oh dear. When I type plot, generic function for plotting R programs, it wants to know the X, if there's a legend, different colors associated with it, blah, 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 blah. We're really simple. So it's just going to plot that tree, and it knows, oh, and then it's going to give it a title, which is nice because then we can tell the difference. So let's plot both of these. Okay, here's our neighbor joining tree. Remember that I used a highly conserved gene, which probably wasn't the best for this example. So it's saying that there is a 3-way split. So Papio anbus, which is a kind of monkey, and then rats and mouse and Homo sapiens and chimpanzees. So chimpanzees and Homo sapiens share a most recent common ancestor with rats, mouse, and with the rat mouse clade, I guess I should say, and this small monkey. So this is our neighbor joining tree. This is just overall similarity. If we go click over, this is our parsimony tree. Here we get a little bit more resolution. So the rat mouse group together, and they share a common ancestor. We saw that in the other one. And then chimpanzee and Homo sapiens are closely related, and then that monkey is on the next one out. And then we get to the rat mouse ancestor. I picked these so we could kind of have an in-group and an out-group scenario. We could put like fish, and it would hopefully fall out here somewhere and not in here. But again, those Hox genes are really, like, even fruit flies are really similar. That's where all that information, like, you know, those, I think we have it, I think I had a PowerPoint slide that said, like, you share this much genetic similarity with bananas. It's because of these, like, genes responsible for living. Those are the Hox genes a lot of times. Okay, then we can, this is really obvious because they're so similar, and because the sequences are so similar, and I only have 5 things. but we can run the scores for each tree, how well supported they are. They actually get the same exact score. It's just because there isn't enough variation. Sometimes when you run this, you get a little bit higher score for the parsimony tree than the other tree because it starts in a different place every time. Sometime in the future, if you get into phylogenetics, we can talk more about tree searching space, but it always kind of starts with a random and then builds a better tree from there, and so that's why the score can change a little bit, but they're largely really similar. Okay, so we did that. That is all you have to do for this assignment. You're going to want to turn in your code, so either this here, yeah, that's good. Copy what's in your console. It's especially good if you're having an issue. I can help you. Screenshot or print these so you can export this as, yeah, look, save as image, and then you can put it in your assignment. And you're going to want to talk about the differences between your neighbor joining and your upgammon tree. This is your parsimony tree. Now, if you don't want to build your neighbor joining tree again, you don't have to, because you should already have one from muscle, so you can compare this tree to your muscle tree as well. Okay, this is all you need for that assignment. Let me show you, just so we're all on the same page. Oops, I opened the wrong internet. That's why that didn't work. Just so we're all on the same page. Oh, no. Okay. Okay, just so we're all on the same page, let's show you where to turn this in. You're going to go to the Tree Thinking tab. And here it is, and it says turn in copy of your R log or your console, screenshots of your neighbor joining and upgammon tree, and then your tree scores. And then you'll discuss the topology of your trees and how it's different and how it feels, which one's more accurate. So in this, I know, based on what I know about these sequences, and because I picked them, that this is much more accurate than this neighbor joining tree, even though they really have the same score. So sometimes you have to go with both math and, instinct. Okay, so to turn that in, I'm just going to click on this, and it's going to take me right to that. Blah, blah, blah. And there's where I can submit everything I need to submit. Also, in case you need help, my FASTA file I used, here's the R and here's the text, so that you can just run it by simply clicking on those different commands and then hitting run. Okay, that's it. Good luck. Thank you.